The training program that you'll soon begin was designed with you, the trainee, in mind. All of the materials were designed to make your job of learning easier, to help you learn faster and better. We believe that you should have ultimate control over what you learn. We believe that you should be informed of the specific objectives to be met in the training program. And lastly, we believe that you should be allowed the time needed to master the subject. Now, before you begin, let me introduce you to the video learning system format and familiarize you with the learning materials. This is an individualized, self-paced program designed so that you can study and learn at your own pace. This means that you can view a lesson more than once if you wish to. You can study at a time convenient for you, and you can progress as quickly or as slowly as you want to. Also, if you feel sure of your understanding of a particular topic, you may choose to skip it and go on to another lesson. The materials consist of 4 instructional modules, each with an accompanying videotape and student guide. The video and print materials support one another and are intended to be used together. For each lesson, there's a set of learning objectives. The objectives tell you what you should learn from the lesson. You'll find them listed at the beginning of each lesson in your student guide. At the end of each lesson is a student activities section. The self-check questions will tell you how well you understand the material just covered. The practice questions will test you on just the information outlined in the objectives. You can verify your answers with the answer key. In order to benefit the most from these training materials, we recommend that you follow a planned procedure. First, you need to become familiar with the operation of the video equipment. When you're ready to begin a lesson, insert the tape into the player and advance it to the lesson according to the counter indicator number given on the videotape label. Turn to the lesson in the student guide and read the objectives. Next, view the videotape lesson. When you've completed the video portion, read the lesson in your student guide. Test your understanding by completing the student activity and check your answers. At this point, you may wish to review portions of the videotape or student guide before going on to the next lesson. When you've completed all 4 modules and feel comfortable with the content, take the post-test and check your answers with the answer key. Your score will tell you if additional review of the material is needed. We think you'll enjoy this system of learning at your own pace and in your own way, and we're certain it will help you in your job. When you've completed the video learning program, we would appreciate hearing your comments. To do this, please call or write the Solar District Service Manager in your district. The remaining 2 lessons in this module describe the Saturn generator package and the gas turbine engine. Lesson 2 will orient you to the package as a whole, identifying major package elements, directional orientation, and generator set applications. Also in this lesson, you'll learn the location and function of the gas turbine engine components. Lesson 3 is dedicated to gas turbine engine theory. You'll learn about the 4 processes that make a turbine work: compression, combustion, expansion, and exhaust.
We're here at the Kearney Mesa facility of Solar Turbines in San Diego, California. This Saturn generator package is just about ready to have the enclosure installed before being shipped to Alaska. The Saturn generator set is designed to generate electricity for 4 major applications. For main power and continuous duty, as this one is. For standby power in case of commercial utility failure. For power in a peaking application when there is maximum demand for electricity. In a peaking application, the unit is run in parallel with the commercial utility. And finally, as power for cogeneration in which the electricity generated is used in any of the applications just listed. In cogeneration application, exhaust heat is utilized for a secondary purpose, such as heating a process fluid or as a direct heating or drying medium. The Solar Saturn generator set is a fully operational package equipped with all accessories necessary for normal operation when connected to a customer's facility. The generator set consists of 4 major elements: the turbine engine, the reduction drive assembly, the AC generator, and the skid base frame. The power plant for the generator set is the Saturn turbine engine. The engine consists of the accessory drive assembly, an air inlet assembly covered by this air inlet duct, the compressor, the diffuser, the combustor, the turbine section, and the exhaust diffuser. The engine is supported on the forward end by a bracket attached to the skid base frame and by the output reduction drive assembly support at the aft end of the engine. The two-stage reduction gearbox in the output reduction drive assembly reduces drive speed from the engine to the generator. The first stage reduces the speed from 22,300 RPM to 6,000 RPM, and the second stage reduces from 6,000 to 1,800 RPM for 60 Hertz and 1,500 RPM for 50 Hertz. The assembly is mounted on the skid base frame by a trunnion-type mount. The next major component is the driven equipment. This is the AC generator, and it's mounted at the rear end of the skid on the base frame. The output shaft of the reduction drive assembly and the input shaft of the generator are very carefully aligned for squareness and concentricity. The shafts are connected by a two-piece shear coupling enclosed in this protective cover. The skid base frame is a welded assembly fabricated from structural steel. The base frame supports the turbine engine, the output reduction drive, and the generator. These major components are installed in an inline arrangement. The skid also mounts many components of the start, fuel, and oil system. An enclosure is usually selected to house the skid-mounted components. Items installed on the enclosure may include ventilation silencers, sound absorption material, and a separate ancillary skid for silencers and filters. The electrical system control console may be remotely located at a customer's selected area. The console houses components that control and monitor the generator set. A remotely installed battery charger and battery rack assembly is usually included with the generator set when the customer does not provide the required DC power source. The electrical system DC circuit breakers are usually mounted on the rack assembly. As you proceed through the video and print portions of this program, you will hear components referenced by their location in relation to the package. It's important to establish just which end of the package is forward and which is aft, which is the right side and which is the left side of the package. To accomplish this, stand and face the generator end of the package. I am now standing at the aft end, looking toward the forward end of the set. On my right hand describes the right side of the package, and my left hand describes the left side of the package. As an example, you can say that the exhaust collector is aft of the air inlet. Or you can say the primary fuel valve is at the forward right-hand side of the package. Up until now, we've been talking about the entire package. Now it's time to talk about the heart of the operation, the turbine engine. The Saturn turbine engine is a single shaft, constant speed, axial flow unit. These terms signify a great deal about the characteristics of this engine. The term single shaft means that there is one continuous rotating shaft supported by sleeve bearings at 3 critical points. The term constant speed indicates the RPM of the shaft will be set at the desired speed to meet predetermined application requirements. This speed is kept constant by a fuel governing system. Axial flow refers to the flow path of the air through the engine. This air path is straight through the engine parallel to the axis of rotation of the shaft, hence axial flow. In the next lesson, the theory of how a turbine engine works will be presented in detail. Now, it is time to become familiar with the major assemblies of the engine itself. The gas turbine engine consists of several basic subassemblies which are connected in line using attaching bolts at the housing or case flanges of each subassembly. Starting at the forward end of the engine, the accessory drive assembly provides input and output drives of required rotational speed through a series of gears. A pinion gear is located on the forward end of the shaft to drive the accessory drive gear train in the air inlet assembly. Mounting pads are incorporated on the accessory drive housing for the main lube and hydraulic oil pump, speed governor, starter assembly, and liquid fuel pump when used. Just aft of the accessory drive, the screened air inlet assembly directs air through a 360-degree path into the compressor. The center of the air inlet housing contains the forward compressor rotor bearing which supports the compressor shaft. An air inlet duct fits over the air inlet assembly and directs air into the assembly. The next assembly in line is the compressor. The compressor is an 8-stage axial flow type incorporating a case and balanced rotor assembly. The case is attached to the air inlet housing. Next is the diffuser section located between the compressor and the combustor. This is where the highest pressure in the engine exists. This pressure is the output of the compressor section and is referred to as compressor discharge pressure, or PCD. From the diffuser, pressurized air goes into the combustor section where fuel and air are mixed, ignited, and combustion takes place. The combustor assembly consists of a case, combustor dome, combustor inner and outer liners, shrouds, and the fuel manifold and nozzle assembly. An igniter plug, compressor discharge pressure air lines, fuel air lines, and fuel drain fittings are installed in the case. Aft of the combustor, the turbine assembly consists of the turbine case, nozzles, a balanced rotor assembly, an exhaust diffuser assembly, and the turbine output shaft. The turbine rotor consists of 3 turbine rotor discs with blades attached to the turbine shaft. The turbine rotor assembly is where the hot gases from combustion are used to turn the shafts of the turbine and generator for sustained operation at constant speed. The turbine shaft is supported on the aft end by a bearing. Part of the structural shell of the engine is formed by the turbine case, which is bolted between the combustor case and the exhaust diffuser. Between the turbine rotor assembly and reduction drive is the exhaust collector. The exhaust section consists of a fabricated exhaust collector and a cast exhaust diffuser whose function is to direct hot exhaust gases to atmosphere or to a heat exchanger. The exhaust collector and turbine case are insulated with stainless steel blankets. The final main subassembly is the output reduction drive assembly, which reduces shaft rotational speed in stages from 22,300 RPM to either 1,800 or 1,500 RPM, depending on the generator frequency. In this lesson, you have been introduced to the Solar Saturn generator package. You have studied the generator set applications, major components, physical orientation, and main engine assemblies. In the next lesson, you will see how these parts are interrelated when you learn the fundamental principles of how a turbine works.
In this lesson, you will learn the basic principles which make the turbine engine a highly reliable and efficient power producer. Turbine engine theory will be presented at a fundamental level and will provide you with the basic concepts necessary for the remainder of the course. The industrial turbine engine is an internal combustion engine which produces horsepower by using the energy of highly compressed air mixed with fuel and ignited under special conditions. It is in the ignition and combustion process that heat energy is produced and is converted into power useful for work. Continuous operation of the engine requires that 4 processes occur: compression, where atmospheric air is compressed; combustion, fuel is added to the compressed air and ignited; expansion, air and combustion gas expand through nozzles; and exhaust, air and combustion gases are discharged into the atmosphere. To begin the process of energy production, air is first drawn into the compressor. Rows of blades compress the air into an increasingly smaller space. After the air leaves the compressor, it enters the diffuser area. In the diffuser, an additional pressure rise occurs. The pressure at the exit of the diffuser is about 76 pounds per square inch at operational speed and full load, right about here. After the air leaves the diffuser, it enters the combustion chamber where either liquid or gas fuel is added to the air. This highly pressurized air and fuel mixture is then ignited by a fuel-fed torch. The combustion process releases the energy of the fuel in a temperature rise in the combustor, and after ignition has taken place, the hot gas expands very rapidly and velocity increases. The average temperature in the combustion chamber is about 1600 degrees Fahrenheit. These hot gases expand through the turbine section, deflect the turbine rotor blades, and rotate the turbine rotor. The turbine rotor then produces the power to turn the compressor and the electrical generator. As the expanding gases flow through the turbine section, the temperature and pressure drops, and they ultimately exit the turbine into the atmosphere through the exhaust collector. Air is the most critical requirement of the turbine engine. The way air behaves explains how the engine is able to produce power. In this portion of the lesson, you will learn some interesting and important facts about air. These facts explain why the turbine engine can use air to great advantage through energy conversion. The turbine engine uses heat and pressurized air to perform work. There are several properties of air which should be kept in mind in order to understand how air and heat are put to work. These properties explain how energy is converted from one form to another. The turbine is designed to take maximum advantage of energy conversion. We know that air consists of minute particles, invisible to the eye, called molecules. Molecules are in constant motion, colliding with other molecules and with the walls of any container which holds them. Temperature is simply a measure of the speed of molecular motion. When air molecules are moving slowly, we measure a low temperature. But when molecules are in rapid motion, the temperature reads high. When molecules are enclosed in a container, some of the molecules will strike the walls at all times. The faster they travel, the more force will be exerted against the wall. This force is measured as pressure. Since temperature is a measure of molecular motion, the molecules will move faster when heat is added. So, heat energy is transferred to energy of motion. But when air molecules move faster, they exert greater pressure. So, temperature and pressure are closely related. In fact, at a constant volume, for each increase in temperature, there is a corresponding increase in pressure. Another property of air which is important to turbine operation is compressibility. If we attach a compressor to our container, we can add more air molecules to those already there. Should we continue to pump air into the container, we would see the pressure rise. It's easy to see why. With more molecules, the numbers striking the wall at any given time increases. Since each molecule exerts force on the wall when it collides, it follows that pressure will increase when more molecules are pumped into the container. So energy has been converted into pressure through compression. Now there is one final but extremely important property of air. In order to understand it, we'll have to take the air out of the container and put it in a pipe. Let's add a reliable, steady air supply which will deliver a constant flow rate to the pipe. Remember that air flows through the turbine engine in a similar fashion. The air has temperature, pressure, and a forward velocity provided by the steady air supply. Now observe the results of constricting the pipe to half its diameter. Since the constriction must move the same amount of air as the larger pipe section, air must move through the reduced pipe faster. Failure to increase velocity in the narrow pipe results in a blockage and reduced flow. But we see that velocity does increase. Energy is required to increase air velocity, and the energy required here comes from the existing air pressure. As energy is converted from pressure to velocity, we see the air pressure drop. When air flows into a constricted flow path, we observe a velocity increase and a pressure drop. If we allow the air to flow back into a pipe of the original size, the flow is now traveling at a lower velocity. Since the velocity of air decreases, excess energy is converted into a pressure increase. When air flows into a larger pathway, velocity decreases and pressure rises. In the turbine engine, the unique relationship between pressure and velocity explains many operating principles. In the compressor, the air is slowed and compressed. In the combustor, the air is heated and then expanded. In the turbine, the air is speeded up to be used to turn the turbine wheels and then is exhausted to atmosphere. Now you will learn about the compressor and how compression is achieved. You'll see how the compressor is designed and study the effects of compression on air. Your understanding of these concepts will help you in dealing with routine troubleshooting and maintenance related to the air system and engine start sequence. The principles of compression are best understood by first looking at the construction of the compressor. The flow path is formed by an annular passage around the rotor assembly. As the air flows along the length of the compressor, the air path decreases in size. Since the path for the air is parallel to the rotor axis, the compressor is an axial flow type. The work of compression is done by several rows of blades similar to the blades of an electric fan. Looking closely, we can see that some of the blades are in stationary rows attached to the case. These are the stators. Other blades, called rotors, are in rows attached to the rotor assembly. When the rotor assembly rotates, these blades move much like a fan. Small amounts of compression occur between each set of rotors and stators. Each pair of rotors and stators is a stage. This compressor has 8 stages. At each stage, the rotors increase air velocity and the stators slow it down. The energy derived from slowing down the speed of air results in a slight increase in pressure. While the velocity of air remains almost steady, the pressure is increasing as it passes through each stage. Each stage multiplies the pressure obtained from the preceding stage. A very small pressure at the first stage quickly becomes a very high pressure at the last stage. Remember that the air path decreases in size along the compressor's length. This permits the compressor stages to maintain the pressure passed along from the previous stages. Now, with an increase in pressure goes a similar increase in temperature. So the air leaving the compressor has gained high pressure and a high temperature. This is done by alternately speeding up and slowing down the air in an ever-decreasing air pathway. The question you may be asking yourself is, how does air movement get changed into pressure? The answer is related to the shape of each compressor blade. Each blade is shaped like an airplane wing or airfoil. Air flowing over the top of the airfoil must travel over a longer path in the same length of time it takes the air to pass across the bottom of the airfoil. To do this, the airflow across the top must increase its velocity. You recall that when velocity increases, pressure drops. This is how a low pressure above the foil and a higher pressure below is obtained. This difference in pressure creates a lifting force that pushes the airfoil towards the low pressure area. Now let's look at the compressor blades again. At the first stage rotor, a low pressure area is created on this curved surface as the rotor rotates. Air from the atmosphere then rushes in to fill this spot. The rotor blade motion increases the air velocity and moves the air into the spaces between the next set of stator blades. Now, whenever air is forced through an enlarging air path, the velocity decreases while the pressure rises. It's at this point in the spaces between stator blades where air is slowed down and we gain air pressure. This is called diffusion, and it is the key principle which makes the compressor work. The space between rotor blades acts as a diffuser too, slowing down the air velocity. Won't the air eventually stop if we keep slowing it down? No, it won't stop because two things are occurring which maintain air velocity. First, the moving compressor rotor blades add energy to the air and force it along to the adjacent stators. You remember that the air path along the compressor's length is decreasing in volume. Let's look very closely at the space between one set of rotors and stators. Here, the shape of the air path is decreasing. In fact, we have a miniature nozzle. This causes the velocity to rise slightly before the air enters the next set of blades. So the nozzle effect is the second way that air velocity is maintained. As the air moves between hundreds of blades on 8 stages, its pressure is multiplied by diffusion and its velocity rises and falls in the process. After leaving the compressor, another pressure rise occurs before the air reaches the combustor. The pathway the air follows is shaped like a diffuser. The diffusion path increases in area and the air velocity slows down so combustion can occur. It is in this diffusion pathway that the final pressure increase occurs. At the rear of the diffuser, air pressure is at its highest level. Since this pressure is most important in monitoring engine performance, it's given a special name, the compressor discharge pressure, or abbreviated in engineering terms, PCD. On the Saturn engine, PCD is measured at the bleed air boss on top of the combustor dome. A PCD gauge is mounted on the engine gauge panel. Before moving on to other engine sections, the compressor operation must be explained further. In previous topics, you learned how the compressor functioned at normal operating speeds. At lower speeds, however, the process of compression isn't nearly as perfect, and if not carefully controlled, it can result in failure of the compressor to pressurize the air. Your instructor for this portion of the lesson is Dick Fowler.
Surge is a condition that can take place in the engine compressor at low engine speeds. It is caused by a blockage of air in the last stages of the compressor. The engine compressor is designed so that at operating speeds, all 8 stages pass on air equally at the same level of efficiency. At low speeds, however, during acceleration and deceleration, the forward stages are able to accept and pass on more airflow than the rear stages can handle. The rear stages then become choked because of their inability to move the large volume of air out of the compressor. The resulting surge condition causes the turbine to heat rapidly to an extremely dangerous level. This will severely affect the turbine components and decrease the engine's lifetime. Let's use the airfoil to explain the low-speed surge. The term stall is normally